instrument. Have you heard about distance of distinct vision? Have you heard this?
No, sir.
Okay. Have you
So
got
distance what, sir?
distinct vision? Distinct.
Vision. Oh, so no, sir.
You have seen movie anytime?
Yes.
In theater, have you seen movie?
Yes.
Where you prefer to sit? Back, no?
Yeah. Yes.
So that this object, when it gives angle to your eye, it will become small. So we will have soothing effect. But if I sit here very close and this is the screen, so बड़ा angle बनाएगा ना, आँख पे strain आएगा. So we want to observe the object clearly at the same time without strain. So that distance is 25 centimeter, which is called distance of distinct vision. Hello? Hello?
Yes.
What is that distance called? Distance of distinct vision. See, our eye is also having lens, na? Natural lens, na? It is eye lens. There are ciliary muscles. That you might have studied
Yes.
in bio.
Yes, sir.
So this focal length can be adjusted, but not beyond certain limit. So for normal eye, if distance is 25 centimeter, then we can see the object clearly. And this position is also called as near point of the eye. So whenever you read in the numerical near point, means where it is placed at distance of distinct vision. So
Yes, sir.
suppose they say object is at near point. What you will understand? Distance of object is 25 centimeter. Okay.
Yes.
Right, first heading, power of accommodation of eye. Power of accommodation of
Yes, sir.
now see, we have studied power of lenses 1 upon focal length. Hello? Hello?
Yes.
So when this is focal length, rise relaxed, then it will be maximum. And when it is stretched, then it goes on decreasing. So up to certain value, this ciliary muscles can be elongated or compressed. Beyond that, it will not function properly, so we have to wear glasses. The power of changing the focal length of the eye is called as power of accommodation. So the power of changing focal length of the eye of ciliary muscles is actually called power of accommodation. Just one line may they can ask you sometimes, MCQ. Right, first line. The power of changing the focal length of eye, the power of changing the focal length of eye is called as power of accommodation. The power of changing focal length of eye is called as power of accommodation. Right. This much.
Yes.
Then write no. Far point means at infinity. Near point means at distance of distinct vision. I'm writing short form DDV. Distance of distinct vision. That is at 25 centimeters. Shall I clear this now?
Yes.
Yes, sir. Yes, sir.
Now, what is visual angle? If this is eye, and here we have lens, this is retina. When the image falls on retina, then only the person can see. Na? So if object is here far, then angle subtended at eye will be this. So image form will be in this zone on the retina. If the object is here, then angle subtended will be very large. So it may either come on the retina or it may go beyond. So angle which an object subtends at our eye is called actually visual angle. So this is suppose one visual angle, this is another visual angle. The angle subtended means made by object at our eye is called as visual angle. Copy this one. Then I will start with what is magnifying power.
Yes, sir.
Now actual optical instrument part will start. First is magnifying power. What is only power of lens? Ability of lens to converge or diverge the rays when it is made to pass through them is called power. And power is 1 upon focal length. Okay? Hello?
Yes, sir.
The magnifying power of an optical instrument. Optical instrument means they will also contain lens only. The magnifying power of an optical instrument is defined as the ratio of angle subtended by image formed by the optical instrument. Angle formed by angles subtended by image formed by optical instrument at eye to the visual angle subtended by object at the unaided eye. Unaided eye means what? Without any instrument. Hello? That means if this is my eye, I don't have any optical instrument. So whatever angle it subtends, that angle is called as angle subtended by the object at unaided eye. Okay? Hello?
Okay, sir.
This much copy. Then three
Yes, sir.
instruments we have to study. It's ray diagram, magnifying power, two cases.
Yes, sir.
Derive expression for magnifying power. Derive expression for magnifying power of simple microscope. Derive expression for magnifying power of simple microscope. So first we require alpha, which is angle on unaided eye, then beta, which is due to that optical instrument. Simple microscope is actually a convex lens where object is adjusted in such a way that it lies between f and p. So we get virtual image. So first we'll find what is alpha. Suppose AB is an object placed at distance of distinct vision and seen directly without any lens, then this angle alpha is called as angle subtended by object on unaided eye. From this figure, can we say tan alpha is approximately alpha because angle is very small and measured in radian? Hello? Can we say that tan alpha
Yes.
is approximately alpha? So alpha is opposite side AB upon adjacent side D. We got first equation. Just draw this first diagram. Consider an object AB to be placed at DDB and seen directly. Let alpha be the angle subtended by object at eye. Therefore, tan alpha approximately alpha equal to AB.
AB upon AD.
Pardon?
So will the denominator be AD or D?
No, no. See, opposite side is AB, na? And this distance is D.
Yes, yes.
Now I will draw ray diagram to get that beta. Convex lens behaves as simple microscope. So if this is focus at 4 centimeter I'm drawing. The convex lens is adjusted in such a way that the object falls between F and P. Same object AB at distance of U is adjusted in such a way that it falls between F and P. To get ray diagram, draw ray parallel to principal axis. It will pass through focus. Passing through optical center remains undeviated. When we produce this backwards, it will meet at some point. That point will give me virtual image A1, B1. Image distance is V. And from here we are observing it. Angle subtended at the eye is as good as at the center of lens. This is beta. So ray diagram follow?
Yes.
Just draw the ray diagram, then I will get that beta and then beta upon alpha to get magnifying power.
Yes.
One second, sir.
Yeah. The object AB is adjusted in such a way that it lies between F and P. Thus, virtual, erect, magnified image A1, B1 is obtained. Let U, V be the object and image distance respectively. Let beta be the angle subtended by image at center of lens, in bracket, that is I. Copy this much.
Yes.
What will be tan beta from this figure? Can I say opposite side AB upon U? Or A1 B1 upon V? Both are same. So from the figure, tan of beta, we can take approximately beta because angle is small, which is AB upon U or A1 B1 upon V. Since magnifying power is ratio of angle subtended by the image to the angle subtended by the object on unaided eye. Alpha we got AB upon D. So I'm taking first one AB upon U so that we can cancel one time. So this is D upon U. This is expression for magnifying power of simple microscope. Now D is fixed. So just by adjusting U, we can increase the magnification. Smaller the closer the object, high the magnification. If U goes away, then magnification will become smaller. Just copy it in this. Then two cases we are doing.
Yes.
Is one object since we are going to see image, so for us image is more important rather than object. First one, image is at DDV. It is also called as near point. So when object is at DDB, we are interested in what will be the magnifying power formula. So image is at DDB. So can I say image B is at DDV but on left hand side? So minus, and object may be again at any position but on left hand side we have used proper convention. Because now we want final answer with proper convention, sign convention. What is Lensmaker's formula? 1 upon f equal to 1 upon v minus 1 upon u. So 1 upon f will be 1 upon v, which is minus d, minus of 1 upon minus q. That is 1 upon f equals to minus 1 upon d plus 1 upon u. I am multiplying throughout by d. Multiplying throughout by d, we get d upon f equals to minus d upon d plus d upon u. So d upon f equal to minus 1 plus d upon u. That means d upon u is 1 plus d upon f. What is d upon u called as?
Magnifying power.
Magnifying power. So that is magnifying power is 1 plus d upon f. Right, first case. See, we have assumed that I is placed close to this. And from this P, we took image distance as P, which is D. And for D, we got 1 plus D upon F, correct? Hello? Hello?
Yes, sir.
But if from this I, this distance is D, then actual distance from center will be what? Whatever is distance of I from the lens, subtract D. No? That means if small d is distance of I from lens, then our B will become not D, but it will become D minus 2. So if they say I is at 2 centimeter away from lens, so in place of D, you will write D minus 2, correct? No?
So we will repeat last.
I'm saying we put V is D. What is V? Distance of the image from the center of the lens, optical center,
Yes.
and we assume that I is very close. But if I is away from where you are observing, then this distance D is not actually V. Then V will become this, na? Which is D minus D.
Yes, sir.
So sometimes they can write this numerical, they can give this numerical. That I is not very close. So if I is at distance small d from lens, then our magnifying power 1 plus t minus d it will become upon f. Okay?
This is case 2.
No, in that case only, na, image we had took this only. I आगे पीछे था. It is not case 2. It is part of that case 1. We are
Okay.
assuming that I is very close. But suppose I is at some distance. Then this V which you have taken D, it won't be D from center. Na? So this
Yes.
is the lens. Okay. V we take from the center, which we are telling it, if it is capital D, our answer will be 1 plus D upon F. But if I is kept slightly away at distance D, then this distance will not be capital D from the center. From I it is D. So from center it will become D minus D. Okay.
Yes, sir.
Now case 2. That means if I is moving away from this lens, magnifying power will increase or decrease? Yes. If I is away, then magnifying power will be more or less? Less, because numerator is decreased. So if I want maximum magnifying power, I must be as close as to the lens. That means almost it will be touching that lens. Then it will be the best one. Next one, image, second case, is at infinity. This is also called as relaxed eye position or far point position, meaning is same. So now final image is at infinity, object is anywhere on the left hand side. We are interested in what is magnifying power of simple microscope. So again by lens maker's formula, since 1 upon f is 1 upon v minus 1 upon u, so 1 upon f will become 1 upon infinity minus 1 upon minus u. 1 upon f is 0 plus 1 upon u. So d upon f equal to d upon u. That is magnifying power is d upon f if image is at infinity. Smaller the focal length, more the magnifying power. Small focal length वाला is used generally by watchmaker. बहुत छोटा लेंस होता है, so that they can see large magnification.
Yes, sir.
Completed?
So do we have to write anything like v tends to infinity?
No, no, no. We have already written that if V is at infinity, then our object may be at any position. We want that condition. So we got by using 1 upon f that d by f.
Yes, sir.
Directly also you can write when image is at infinity, object has to be at focus. So u का जगह पे f ही आने वाला. Everybody has done?
Yes, sir.
Now magnifying power of compound microscope. Magnifying power of compound microscope. Again, first you find alpha, then by ray diagram get beta, then ratio of beta and alpha. So consider an object AB situated at distance of distinct vision D and seen directly by eye. Then tan alpha will be approximately alpha, which is opposite side upon adjacent side. So consider an object AB at D, D, D and seen directly. Let alpha be the angle subtended by object at eye. Therefore, tan alpha approximately alpha equal to AB upon D. Copy this. ray diagram I'm explaining. Be careful. Draw later on. First you see how I have done, so that it will be easier for you to manage in the exam. First I'm drawing principal axis, because compound microscope has two lens. One is called objective, other is called eyepiece. Objective is of smaller focal length and eyepiece is of larger focal length. This is principal axis. Objective of small focal length and eyepiece of larger focal length. Objective. This is eyepiece. Now, object is placed slightly beyond focus so that we get magnified image, which will be real, and on other side. So this is suppose f naught. If you take this as 2 centimeter, here also at 2 centimeter mark f. This is called first focus, f naught dash. This is object is placed slightly beyond f naught. Same object AB is placed slightly beyond f naught. So to get ray diagram of this, we have to draw one ray parallel to the principal axis. It passes through focus. And passing through optical center will remain undefined. Suppose we are getting here image. Objective. This is the real image A1, B1 of object created by objective. And this distance is U naught. Distance of object from objective is U naught. And image is B naught. Complete only this much. First part of ray diagram. Just 1 minute, I complete this and we'll be back.
Yes.
Yes, completed, no? Hello, completed to this?
Yes, sir.
Now we can adjust the IPs. So by adjusting IPs, the image A1 B1 is tried to be kept in the between F and P, so that we get again magnified and virtual image on the same side of object. IPs we can adjust. We adjust in such a way that this A1 B1 behaves as object of IPs lies between its focal length and P. So to get its image, we have to draw ray parallel to principal axis. Suppose its focus is here. Take the focus of eyepiece at around 5 centimeter. This I had taken 2, so that our diagram will come appropriate in our book. Ray parallel to principal axis will pass through focus. And passing through optical center will remain undeviated. Passing through optical center remains undeviated. These two rays, if I produce backward, wherever they meet, that is my virtual image. So this is that final, it can come anywhere. A2, B2 is final image, its distance is PE from eyepiece, and this will become UE from eyepiece. Here we are placing eye very close to the lens. Angle subtended is beta. Now complete this ray diagram.
Yes, sir.
Done? Shall I clear it now? Can you tell me what is distance between objective and eyepiece?
Pardon?
What is distance between objective and eyepiece? VO plus UE, no?
Yes, sir.
That is also called as length of microscope. So I'm clearing this diagram and doing that magnifying power. Can you tell beta is now A1 B1 upon UE, or it will be A2 B2 upon VE from the diagram? This opposite side upon this adjacent side, or this opposite side and this adjacent side, which is nothing but VE.
Yes.
The ray diagram to obtain final image is as shown. The object AB is placed at distance u0 slightly beyond f0 and real magnified image a1b1 at distance v0 is obtained. This image behaves as object for eyepiece. The eyepiece is adjusted in such a way that A1 B1 lies within focus and pole of eyepiece. Let UE be the distance of this object A1 B1 from eyepiece. The magnified, virtual, erect image is obtained at distance BE from eyepiece. Just write this much. Therefore, from the figure, tan beta, which is approximately beta, is A1 B1 upon UE, which is same as A2 B2 upon BE. Magnifying power M is equals to beta upon alpha. So beta is A1 A1 upon UE. Alpha is AB upon D. So we can say A1 B1 upon UE into D upon AB, which is A1 B1 upon AB into D upon UE. So, what is the ratio of height of image to the height of object called as? Linear
Sir, yeah,
magnification.
can you?
Ratio of height of image to the height of object is called as what?
It's magnification.
Linear magnification. So I can write MO. And this is we are getting magnifying power of eyepiece, where MO equal to linear magnification of objective, and ME is magnifying power of eyepiece. So sometimes they can ask, prove that magnifying power of compound microscope is product of linear magnification of objective and eyepiece. Yeah, complete till this. Since M naught can also be written as mu naught upon U naught for real image. So we can say magnifying power is minus mu naught upon U naught into D upon U. Case 1. Same concept. Image is at distance of distinct vision. Therefore, M will become minus V naught upon U naught, and for eyepiece, we get 1 plus D upon F of eyepiece. Okay, because already we have proof for simple microscope, so directly you can write.
Yes, yes.
This minus V naught upon U naught, you can also write in F and U. So this is F naught upon U naught minus F naught into 1 plus D upon F. Or we can write like this. In terms of F and U also you can write. First case clear? Next. If case 2, if image is at infinity, that means relaxed eye position or far field, then magnifying power is minus mu naught upon U naught D upon U E, which became D upon F here. or we can write same f naught upon u naught minus f naught d upon f p. Right. The second case.
So,
Yes.
so what have you written if final image is at?
Infinity. If final image is at infinity, that means this UE must be at focus, no? Because when object is at focus, then image comes at infinity.
Yes, sir.
That's why I wrote if infinity, then UE is FE.
So then won't it be modulus FE?
It's understood. Both are in modulus because it can't be negative. We are measuring distance. Completed?
Yes, sir.
Third one. It is called astronomical telescope or refracting telescope. Astronomical telescope, also called as refracting telescope. I want its magnifying power. So four instruments we have to do: simple microscope, compound microscope, astronomical telescope and refracting, and last one is reflecting telescope. So this time you cannot place object at distance of distinct vision because astronomical telescope means object is also far. You can't keep it at distance of distinct vision, that is 25 centimeters. So in this we have to draw ray diagram, and from that ray diagram itself we'll get alpha and beta.
But image will be at one point, right?
Image will be at?
Image will be at a point, right?
No, if the object in the second case comes at focus, then image will be at a point. Otherwise it will be enlarged image. Image will be at a point means what?
So because object distance is large,
Uh,
so then the
see,
image will
see,
be,
1 minute, 1 minute. We are not using one lens here. We are using two lenses. So first one will give you object of smaller size, and then next will be giving in magnified image. You are telling if the object is at infinity, image is point. That way you are saying, no?
yes, sir.
But here we are using two lens, no?
So
So
first object will be diminished and second will,
and then will be magnified.
okay.
Here the objective size is more, so that more light can fall on that aperture, because object is at very far distance. So this is objective of larger focal length. Now object is at very large distance. So in this case, if object is at very large distance, then rays will be parallel to themselves but making small angle with principal axis. That is called para-axial rays. So we are drawing rays coming from object which is very far distance. So this will be the ray making very small angle with the principal axis. Second ray will be parallel to the first one. After refraction, it will be passing through a point which is in focal plane. This ray will pass to the point in focal plane. That's why it won't be point but very small sized image. This is alpha. Angle subtended by the object at objective is called alpha here. This side by vertically opposite angle alpha. And this is that small sized image A1 B1 of object AB, which is at very far distance. Then eyepiece is adjusted in such a way that A and A1 B1 lies at the within the focus of F and within F and P. So again we'll get virtual image. Eyepiece is of small focal length. This is adjusted in such a way that it lies between hello?
Yes.
See, if we
Yes,
adjust
sir.
in such a way that final image also goes at very far distance, then this will become FE. If we adjust in such a way that object distance is FE, image distance, this is nothing but at focus FO. So in case final image is at infinity, these two rays are parallel, then we'll get the image also going at very far distance, that is close to infinity. So here there will be two possibilities. Either image is at infinity or image is within objective and eyepiece. So if the object A1 B1 is adjusted in such a way that it lies at focus of eyepiece, then image will go at infinity. So this is one case. This angle is beta. Just draw ray diagram. Shall I again show you the ray diagram? Hello?
The rays for the second image, they are parallel.
Finally it will be parallel. Just take one precaution. If this is coming at 2 centimeter, this focus you mark at 2 centimeter, then it will be perfect. Then it will be perfectly appearing parallel.
Yes, sir.
So in this case, can I say alpha will be A1 B1 upon F4 and beta will be A1 B1 upon Fe?
Yes, sir.
The ray diagram is as shown above. Let object be at very far distance. Hence, A1 B1 will be image in focal plane of objective. Let alpha be the angle subtended by object at objective. Let VO equals to FO. Now A1 B1 behaves as object for eyepiece. It is adjusted in such a way that it lies at focus of eyepiece, that is at FP. Hence, image is obtained at infinity. Let beta be the angle subtended by final image at eyepiece. Just complete this much, then just 3 more lines to complete first derivation.
One second.
Done.
No, sir.
Complete. आराम से.
Yes, sir.
Therefore, alpha equals to A1 B1 upon FO. Beta equals to A1 B1 upon Fe. So magnifying power comma m equals to beta upon alpha. This is A1 B1 upon Fe divided by A1 B1 upon FO. A1 B1 A1 B1. M equals to F4 upon F3. Completely done.
Yes, sir.
Completed. Today we'll stop here. Just revise and keep this much. Two conditions we have to do in this. And then will come reflecting telescope, and after that resolution power of simple microscope telescope. That will complete optical instrument part. So in one lecture we'll be able to complete entire theory. Then I will begin with only numericals and MCQ, so that our entire first ray optics wala part is over. Exam date is not yet declared.